We're going to calculate the derivative of x squared with respect to x. Maybe a little bit more prosaically, I want to know, how does wiggling x affect x squared? There's a ton of different ways to approach this. Let's start by looking at this numerically. So let's start off by just noting that 2 squared is 4, and I'm going to wiggle the 2 and see how the 4 wiggles. Instead of plugging in 2, let's plug in 2.01. 2.01 squared is 4.0401. I'll just keep on going with some more examples. 2.02 squared is 4.0804. 2.003 squared, say, is 4.012009. Okay, so those are a few examples. I've wiggled the inputs, and I've seen how the outputs are affected. And of course, all the outputs are close to 4, right? But they're not exactly 4. When I wiggled the input from 2 to 2.01, the output changed by about 0.4, and a little bit more, but that's a lot smaller. When I wiggled the input from 2 to 2.02, the output changed by about 0.08, not exactly 0.08, but pretty close to 0.08. And when I wiggled from 2 to 2.003, the output changed by about 0.012, and a little bit more, but it's close. Now look at the relationship between the input change and the output change. The input changed by 0.01, the output changed by 4 times as much, about. The input changed by 0.02, the output changed by 4 times as much. The input changed by 0.003, the output changed by about 4 times as much. I'm going to summarize that. The output change is the input change magnified by 4 times. Right? The input changed by some factor, and the output changed by about 4 times that amount. Let's see this at a different input point. Instead of plugging in 2, let's plug in 3 and see what happens. So 3 squared is 9, but what's, say, 3.1 squared? That's 9.61. Or what's 3.01 squared? Well, that's 9.0601. Maybe wiggle down a little bit. What's 2.99 squared? That's close to 3, but wiggling down by 0.01. That's 8.9401. Now let's see how much roughly the output changed by. When I went from 3 to 3.1, the output changed by about 0.6. When I went from 3 to 3.01, the output changed by about 0.06. And when I went from 3 down to 2.99, the output went down by about 0.06 again, a little bit less. Now, what's the relationship between the input change and the output change? Well, here, the input changed by 0.1, the output changed by 0.6, about 6 times as much. Again, the input changed by 0.01, the output changed by about 6 times as much. And when the input went down by 0.01, the output went down by about 6 times as much. So again, we're seeing some sort of magnification of the output change to the input change, but now it's magnified not by 4 times, but by 6 times. So the important lesson here is that the extent to which wiggling the input affects the output depends on where you're wiggling. If you're wiggling around 2, the output is being changed by about 4 times as much. If you're wiggling the input around 3, the output is being changed by about 6 times as much. Instead of doing just a few numerical examples, let's generalize this by doing some algebra. So I'm starting with x squared, and I'm going to wiggle x and see how x squared is affected. So instead of plugging in x, I'll plug in x plus something. Let's call the change in x h. Now I want to know, how is this related to x squared? Well, I can expand out x plus h squared. That's x squared plus 2xh plus h squared. So when I wiggle the input from x to x plus h, how is the output being affected? Well, the output is the old output value plus this change in output value, 2xh plus h squared. Now, h squared is pretty small. When h is small, h squared is really small. So I'm going to throw that away for now and just summarize this by saying that the output change is 2xh and the input change is h. Now the derivative is supposed to measure the relationship between the output change and the input change. So I'm going to take the ratio of the output change to the input change, and 2xh over h is 2x, well, as long as h isn't 0. This is the ratio of output change to input change, and that makes sense, right? Think back to what just happened here a minute ago when we were plugging in some nearby values and seeing how the outputs were affected. When I was wiggling the input around 2, the output was changing by about twice 2. When I was wiggling the input around 3, the output was changing by about twice 3. Right? 2x is the ratio of output change to input change. If the algebra is not really speaking to you, we can also do this geometrically, like drawing a picture. Here's a square of side length x. The area of this square is not coincidentally x squared. Now, I want to know the derivative of x squared with respect to x. I want to know how changing x would affect the area of this square. Now, let's see this. Here's another square. This is a slightly larger square of side length x plus h. H is a small but positive number. So how does the area of this new square compare to the area of this old square? Let me put the old square on top of the new square, and you can see that when I change the input from x to x plus h, I gained a bit of extra area. The derivative is recording the ratio of output change to input change. So I want to know what's the ratio of this new area as compared to just the change in the input, h. So let me pull off this extra area. There's the extra area. It's this L-shaped region. How big is this L-shaped region? Well, this short side here has side length h. This side length here is also h. This is the extra length that I added when I went from x to x plus h. This inside has length x, and this inside edge has length x. Now I want to know the area of this region. To see that, I'm going to get out my scissors and cut this region up into 3 pieces. Now here's one of those pieces, and here's another one of those pieces, and here's the third piece. So these are the 2 long, thin rectangles, and they've both got height h and length x. I'm also left with this little tiny corner piece, and that little tiny corner piece has side length h, and the other side is also length h. It's a little tiny square. Well, in the limit, this little tiny corner piece is infinitesimal. I'm going to throw this piece away, and most of the area is left in these 2 long, thin rectangles. If I rearrange these long, thin rectangles a bit, I can put them end to end. They've both got height h, so I can put them next to each other like this, and their base is both length x. So how much area is in this long, thin rectangle? Well, its height h, its width is 2x. So the area is 2x times h. Now this is the additional area, excepting for that little tiny square, which we gained when I changed the size of the square from x to x plus h. So the change in output is about 2 times x times h. The change in input was h. So the ratio of output change to input change is 2 times x. Maybe what we're doing here seems a little bit wishy-washy, not really precise enough. But we can also calculate the derivative of x squared with respect to x by just going back to the definition of derivative in terms of limits. Carefully, f of x is x squared, and the derivative of f is by definition the limit as h approaches 0 of f of x plus h minus f of x, the change in output, divided by h, the change in input. In this case, f of x plus h is just x plus h squared, and f of x is just x squared, and I'm dividing by h. Now I can expand this out. This is the limit as h approaches 0 of x plus h squared, which is x squared plus 2xh plus h squared minus x squared over h. Now I've got an x squared minus x squared, so I can cancel those, and I'm just left with the limit as h approaches 0 of 2xh plus h squared over h. More good news. In the limit, I'm never going to be plugging in h equals 0, so I can replace this with an equivalent function that agrees with it when h is close to but not equal to 0. In other words, maybe a little bit more simply, I'm canceling an h from the numerator to the denominator. So 2x h over h is just 2x, and h squared over h is just an h. Now what's the limit of this sum? Well, that's the sum of the limits. It's the limit of 2x as h approaches 0 plus the limit of h as h approaches 0. Now, as far as wiggling h is concerned, 2x is a constant, so the limit of 2x as h approaches 0 is just 2x. And what's the limit of h as h approaches 0? Well, what's h getting close to when h is close to 0? That's just 0. So this limit is equal to 2x, and that's the derivative of x squared. What that limit is really calculating is the slope of a tangent line at the point x. And we can see that it's working. This is the graph of y equals x squared. At minus 4, the slope of the tangent line is minus 8. At 2, the slope of the tangent line is 4. And at 6, the slope of the tangent line is 12. There's a ton of different perspectives here. We've been thinking about the derivative of x squared with respect to x numerically, algebraically, geometrically, going back to the definition of derivative in terms of limits, looking at it in terms of slopes of tangent lines. What makes derivatives so much fun is that there are just so many different perspectives on this single topic. No matter how you slice it, we've shown that the derivative of x squared with respect to x is 2 times x. Maybe you like algebra, maybe you like geometry, maybe you just like to play with numbers. But no matter what your interests are, derivatives have something to offer you.